Okay, so I know seems like an eternity since we've talked about energy. So we got 3 weeks left, but we actually only have 14 class periods because that Thursday and Friday are like the final schedule, okay? So your quote final is going to be finishing up the lab final. So you're going to take your written final on Tuesday of that last week. I'll introduce the lab final on Wednesday. You guys have 2 days, so I'll introduce that on Wednesday. And then that last day, you'll finish up that lab final. So that last week, we'll review for the final on Monday, and that's comprehensive over everything. So we'll review on Monday, take the written final Tuesday, start the lab final Wednesday, and then your lab final is either going to be due Thursday or Friday, whichever day we have. I think we have this on Friday, I don't remember. So in between then, we've got to figure out, finish energy. So the test over energy is going to be this Thursday. Okay, so we have 2 broad ideas of energy to deal with. What we call perfectly elastic collisions and center of mass. We'll deal with that today. Tomorrow we're going to deal with rotational energy. Then Wednesday review, tests on energy on Thursday. Okay, so that's how this week is going to play out if you want to plan accordingly. Okay, so let's talk about the oscillating spring. So first off, as the mass oscillates, did it accelerate?
Yeah.
Absolutely it did, okay? Did it ever have constant velocity? No, it was always either speeding up or slowing down. And the only way something can accelerate is if you have an imbalanced net force, okay? So what are the 2 forces that are acting on that mass as it oscillates? So you have gravity pulling it down, and then you have the force from the spring acting upward, okay? Which of those 2 forces is constant? Gravity. So this one won't change. This is F equals Kx, which is the spring constant. So when is the force from the spring at its minimum? At the top or at the bottom? Top. So when you're up here at the top, the force of gravity is bigger than the force from the spring. That's what allows it to fall. When you're at the bottom, the force from the spring is bigger than the force of gravity. That's what makes it accelerate upward. Okay? Seem reasonable. So if at the top, gravity is bigger than the spring, and if at the bottom, the spring is bigger than the gravity, at some point, what do you know about those 2 forces?
Equal.
They're going to equal each other out. Where do you think that might be? In the middle. So that's when your net force is going to be equal to 0, because that's when you're not going to have. That's when you're not going to have any acceleration, because that's at that equilibrium point. Okay, when it crosses the middle point. Okay. So you have 3 types of energy. You have us, you have UG, and you have KT. KT is the only one that goes to 0 up at the top and the bottom, because your velocity goes to 0 because you're changing direction. Cool. Okay. Now, let's talk about the graph, because if the graph is wrong, about everything else is going to be wrong. So you're going to have force here, and you're going to have elongation here, you're going to have some data points, and you're going to draw a line of best fit. Okay? Now, follow the instructions as I've laid them out. Okay? So I tell you, find your maximum elongation. That's that asterisk, whatever that maximum elongation is based upon your data. Probably something around 0.2. It's an ish, but it's probably something around 0.2. So you're going to come over here. Whatever that maximum elongation is, you're going to draw a line straight up. Okay? Where it crosses the line of best fit, not necessarily the data point that corresponds with that. You can only use that 14.7 newtons if it actually goes through 14.7 newtons, which typically it doesn't, okay, because it's a line of best fit. So over here, you're going to write down whatever that elongation is in that last bottom right column, however many meters that is, and then however many units of force that is based upon the line of best fit, okay? Not the data point, where it crosses the line of best fit. Now, when you get over here on this question number 9, it says, you want to find the average force exerted on the spring based upon the graph. Here's the easiest way to do that. What's the initial force? 0. Then you're going to know what the other force is based upon that. There's your two values of force. 0 and that value up there. Okay? Then just divide that by 2. So basically take your force that matches up with that point of maximum elongation, add that to 0, mathematically difficult, and then divide that by 2, and there's your average force. Okay? Got it. Cool. Any other questions on the lab? We good? Once, twice, sold. Get that handed in. Staple the graph to the back.
Because I got my slope. Joe, what did you get for your K value? Okay, me and Michael got similar and you.
What value?
It's like 65.38.
Right, I used 0, and then maximum elongation for my line.
You were doing the graph wrong, you selected a point that's not right.
Yeah, somehow. Wait, the load point.
Let me just. Plotted a point.
He drew a graph,
He drew a graph. Plotted a point of box short.
Okay.
Like, I determined it using 2 points, but when I use it with those points, it doesn't give me the same number.
How long is the test on 32nd?
Mr. Brigham, what are we doing next Monday?
Gas laws.
I'm determining whether or not I should go to jail.
Oh, go to the jail. Jail is so fun.
What's this? Game set?
Jail is so fun.
Jail is good.
I mean, I'll record the lecture.
There's 3.
Aren't you guys going to the courthouse too?
Gay Lusak's law. Being serious, bro. You can put that's what we're gonna learn next week. Gay Lusak's law.
Oh,
Wait, you guys go to
Gay Lusak's law, bro.
Yeah, wait, are you guys going
Don't play with me if you don't know Gay Lusak's law.
So
Yeah.
you're guys are
Let me give you a hint.
I'm not
Ask
Gay
people
Lusak's
that
law.
were in jail. What would you have done? Skip class or gone to visit the jail? I guarantee you, they all would have said, oh, I would have skipped
Like you have like a
class.
middle name and a last name, so it's
I'm
Gay
just saying.
so if I
How would you
don't,
know if you didn't go to the jail?
I'm just saying.
so if I don't skip class, then I won't go to jail.
I'm just saying. You interpret that however.
the trial back.
Okay, so,
It's been on.
okay, so I'm gonna go through a very, very long derived equation. Do not write it down, okay? I'm even gonna leave out big steps in this process, okay? Don't write it down. I'm never going to expect you to derive these equations, okay? Don't write it down. Don't sit there and go, Burkamp, oh, do we have, no, don't. If you want to, you can, but you don't have to. So what we're gonna deal with is what's known as perfectly elastic collisions. So in perfectly elastic collisions, you conserve 2 things. You conserve energy, and you conserve momentum. Okay? Now, momentum is always conserved, because momentum is a one-trick pony. Okay? Momentum is momentum is momentum. Okay, yeah, you can have angular motion, but that's not what we're going to talk about. So we're going to assume that the momentum is always going to be conserved. The tricky part of energy is that energy can take on so many different forms. So if I dropped this ball, and if that was a perfectly elastic collision, it would bounce back up to the exact same height every time, okay? I would lose no energy to sound, to vibrations, nothing. But that's the great dissipator. So when you hear this, it makes sound, or when the collision occurs, basically the chihuahuas that make up the golf ball don't like being compressed. They don't. And they go, yip, yip. And that costed energy. So anytime you make the chihuahuas angry, it costs you energy. Now, but sometimes that's good. So let's say you go outside your car and you've lost your mittens, okay? But it's cold. So what are you gonna do? You're gonna rub your hands together. Cool, okay? You're making the chihuahuas unhappy because the chihuahuas that make up this hand don't like the chihuahuas that make up this hand. And when you force them to rub past each other, they basically go yip, yip, yip across your hand because they don't like each other. And the yip, yip, yips, instead of sound, are photons. Photons carry energy, which carry that thermal energy. So when you rub your hands like this, it's because you've made the chihuahuas unhappy. So chihuahuas unhappy, they go yip, yip, yip. Your hands warm up, okay? So in a perfectly elastic collision, and I would have to tell you that it is a perfectly elastic collision, okay? I would literally have to tell you it's a perfectly elastic collision. Otherwise, it's not, because this is like an idealized situation where we lose no energy to sound, to the chihuahuas, nothing, okay? Now, I'm going to start to go through this. Don't write this down. I'll show you the process, though. So we're going to start with the energy side of this first. So we're going to have two things. We're going to have the kinetic energy of the target plus the kinetic energy of a bullet is going to equal the new kinetic energy of the target plus the new kinetic energy of the bullet. Okay? Target, boom, hits a bullet. There you go. Okay? Target bullet. So any kinetic energy is just going to be 1/2 mass times, that's the mass of the target, times the velocity of the target squared, plus 1/2 mass of the bullet times the velocity of the bullet squared. And that's going to equal 1/2 mass of the target times the new velocity of the target squared, plus 1/2, that's why I said don't write this down because it's very arduous, okay? Times the mass of the bullet times the new velocity of the bullet squared. Cool. Got it. Great. Now, I hate fractions, so what am I going to do? Multiply everything by 2. Through the miracle of modern math, the fractions go away. Okay? Now, the next thing I want to do is I want to get all the targets on one side and I want to get all the bullets on the other side. Okay? So, I'm just going to take mass of the target, okay, times the velocity of the target squared, minus the mass of the target times the new velocity of the target squared, and that's going to equal the mass of the bullet times the velocity of the bullet squared, minus, that's the new velocity, minus the velocity of the bullet squared. Okay, and there's the mass of the bullet. Okay, cool. All I did was combine terms, nothing earth-shattering at this point. Now, at this point, I want to factor out a mass, okay? So, I'm going to have the mass of the target times Vt squared minus V prime t squared equals the mass of the bullet times Vb prime squared minus Vb squared, okay? Again, nothing earth-shattering. Now, we're going to step back and go back to Algebra 1, okay? If I ask you to factor x squared minus 25, what would you get? Quantity x plus 5, x minus 5, right? Old school, difference of squares, right? Okay? Old school, remember this, okay? Like, we never saw that before, Mr. Burkamp, really? So I'm gonna do the same thing here. I'm gonna rewrite this as velocity of the target minus the new velocity of the target times the velocity of the target plus the new velocity of the target equals, and that's times all of this, and then the mass of the bullet times the velocity of the bullet minus the velocity of the bullet and the velocity of the bullet plus the velocity. Okay? So all I did was just factor stuff out, okay? Nothing unusual. Now, I'm gonna leave that here for a second, okay? I'm gonna leave that here. Now, I'm gonna deal with momentum, okay? So the momentum one is actually simpler because there's nothing squared, okay? So the momentum's simpler. So this is just gonna be the momentum of the bullet plus the momentum of the target equals the new momentum of the bullet plus the new momentum of the target, okay? Not a big deal, same old school. We're gonna do the same thing. Mass of the bullet, velocity of the bullet, plus the mass of the target, velocity of the target, equals the mass of the bullet, new velocity of the bullet, plus the mass of the target, new velocity of the target. Now I'm gonna do the same thing. So I'm gonna move all the bullets over here and factor that out. Okay? And then I'm gonna do the same thing over here. Mass of the target, velocity of the target minus, okay? Velocity of the target. Okay? Cool. So now, since these two things have to be conserved, okay? And there has to be an equality that exists in between these two, I'm gonna take this energy and I'm gonna divide it by what happens with the momentum. So I'm gonna say this is gonna be the mass of the target times, actually that should be plus and minus, because otherwise this isn't gonna work. So minus velocity of the target, and this is gonna be the mass of the bullet times the velocity of the bullet, okay? So here's what's gonna happen. The masses are gonna cancel out, I don't have to worry about these, and I'm gonna lose one of these terms. So, here's what's important at this point, is that, and I'm gonna rewrite this because it's gonna make more sense later on. Velocity of the bullet plus the new velocity of the bullet equals the new velocity of the target plus the original velocity of the target. So I just moved that over there because that's typically how it's done. You deal with the bullet on one side and the target on the other. So here's what's gonna be important, okay? If it's a perfectly elastic collision in terms of momentum and energy, the sum of the two velocities of the bullet has to equal the sum of the velocities of the targets, okay, before and after, okay? So that's a simple way that you can check, hey, does this make sense? Now, if you do a whole bunch of other recombining, which I'm not going to, here's the heart and soul of what you need, okay? This is what you need. So the new velocity of the bullet is going to equal the mass of the bullet minus the mass of the target times the original velocity of the bullet divided by the sum of the masses. And then the new velocity of the target is going to equal 2 times the mass of the bullet times the velocity of the bullet divided by the sum of the masses, okay? If you ever specifically need this equation, I will give it to you, okay? Like on the assignment, this is at the bottom of the assignment, okay? Do not memorize it. If you actually need to do specific equations or calculations with this, I will give you this equation. Don't waste brain cells memorizing it, okay? What you do need to know, oh, it's a perfectly elastic collision, we're going to conserve both energy and momentum. Now, let's talk about this. So we're going to look at 3 scenarios. Scenario number 1, you're going to have a small bullet running into a big target, okay? Now, if this is going to happen, you're going to be talking about the difference between the mass of the bullet and the mass of the target. Mathematically, what's going to be the sign of the new velocity of the bullet? Positive, negative, or zero? Negative, what?
Target is bigger.
Yeah, because if I take the small mass of the bullet and subtract a big mass of the target, I'm going to get a negative number. Velocity of the bullet's a positive number. So what that means is that the new velocity of the bullet is going to be a negative value. So what did the bullet have to do?
Bounce.
Change direction, it has to bounce off, okay? So this is what happened like when Rutherford shot the helium nucleus at the gold nucleus. The gold nucleus was very, very massive. The helium nucleus was very, very light. So it hit and it actually bounced back because of the fact that that's like an idealized situation. Okay, what if the mass of the bullet is equal to the mass of the target?
No loss.
What does that mean?
It didn't.
What's the bullet going to do?
Stop.
Bullet's just going to stop. What's the target going to do?
Don't move.
Not moving.
Doesn't do it. Has the same velocity as gold.
So, if momentum has to be conserved and the bullet stops, what does the target have to have? The exact same momentum, right? So if the bullet stops, the target has to have the exact same momentum and kinetic energy as the bullet, because it all gets transferred, okay? Makes sense, okay? Third option, the mass of the bullet's really big compared to the mass of the target. So we're gonna have a big bullet hitting a small target.
Goes through.
What's the bullet gonna do? The bullet's gonna keep going. So the bullet's gonna hit, but it's gonna keep going. But what's it gonna have to do? Speed up or slow down? It's gotta slow down because it's gonna lose some momentum and energy to the target. Okay? Cool with that. All right, Ava, stop that camera. Let's go to the back.